Our second example is the one shown in the PowerPoint slide on the right there, pulling a box up a ramp. Example problem. It reads, a 20 kilogram box rests on a frictionless ramp with a 15-degree slope. The mover pulls on a rope attached to the box to pull it up the incline, and the rope makes an angle of 40 degrees with the horizontal. As the box moves with constant velocity up the ramp, what is the force? And what is the normal force on the block? Okay, so let's go ahead and work through this. I start by picking out the things that are given. So we have a mass of 20 kilograms, a theta of the ramp is 15 degrees, and the theta for the tension is 40 degrees. The velocity is constant, which means the acceleration is equal to 0. And that therefore means that we can make good use of Newton's second law in the special case where the net force is equal to 0. We are asked to find the force, the magnitude of it, and the normal force. So the tension on the rope and the normal force. Those are the two things we're supposed to find. So net F vector is equal to 0. Let me go ahead and first make a little sketch here. Even though it's on the slide, I always like to redraw the sketch because sometimes when I'm drawing it, I notice different things. So the ramp makes an angle of 15 degrees. The tension in the rope makes an angle of 40 degrees, but not with respect to the slope. It makes a 40 degrees with respect to the horizontal. And then there's the normal force, which is going to be perpendicular to the surface. The free body diagram is the important tool that we use here. So the free body diagram means that my object, which is the box, is a particle with the forces acting on it. So its weight is pointing down, the tension in the rope is up at 40 degrees. And then the normal force is 15 degrees away from the y-axis. Okay. So I've labeled things F sub n for the normal force, T is the tension in the rope, and W is the weight of the object equal to the mass times the acceleration due to gravity. I sometimes find it helpful to redraw the vectors separate, and I see that they didn't really come out very well in the screencast. I'm sorry about that. So what I'm showing here is that the tension in the rope has an x component and a y component, and I can use trigonometry to figure out what each of those things are. And the same is true for the normal force. So it is, up and to the left. It has an x component and a y component. And it makes that angle with respect to the vertical axis. So we're going to make use of the vector nature of Newton's second law, which means that the x components and the y components of the net forces are equal to 0. So the x components, you can see, are made up of just the tension in the x direction and the normal force in the x direction. So that's t cosine theta t minus F sub n sine theta r. Theta r is the angle of the ramp. Okay, so if I solve for F sub n, it's going to be equal to t, that should be a t there, cosine theta t divided by sine theta r. Now I can go on and work with the y components. Net Fy is equal to 0, so I'll have a component of the normal force in the y direction plus a component of the tension in the y direction minus W. Note here that I've accounted for the directions in the signs of things, and so even though W is pointing down, it's going to be a positive number. I put the minus sign there. So I'll have F sub n cosine theta r plus t sine theta t minus mg. All this is equal to 0. And I can plug in my expression from the x components for the normal force. So now I have an equation written where 0 is equal to t cos theta t divided by sine theta r, and I can solve this for t. That should be sine theta t I'm sorry, yeah, sine theta t plus cosine theta t divided by sine theta r cosine theta r. Sorry about the clarity of those expressions. If I plug in the numbers, pay attention to degrees and significant figures, I get that the tension is equal to 56 newtons. And I can plug this back into the equation for the x components to figure out what the normal force is. Let me just clarify what this equation is supposed to look like. Okay, I'm going to do it with a slightly smaller font. So T should be equal to mg times the quantity, let's see, big thing here, 1 divided by sine theta t plus cosine theta t divided by sine theta r times cosine theta r. So remember, theta t is the angle that the rope makes, and theta r is the angle that the ramp makes. Of course, mg is the mass times the acceleration due to gravity, and so it should have units of newtons.